Welcome to my channel. Today, we're going to dive deep into support vector machines, one of the most powerful and elegant algorithms in classical machine learning. If you're preparing for interviews or want to truly understand how SVMs work under the hood, you're in the right place. So let's start with the fundamental problem that SVMs solve: binary classification. Imagine you have a dataset with two distinct classes of data points. On our visualization, you can see blue circles representing one class and orange squares representing another. These points are scattered across a two-dimensional feature space, with each axis representing a different feature of our data. Now here's the key question. If we want to draw a line that separates these two classes, how do we choose the best one? As you can see, there are multiple possible decision boundaries we could draw. Each dashed line represents a valid separator that correctly classifies all the training points. But which one would perform best on new, unseen data? This is exactly the question that SVMs answer in a mathematically elegant way.
The key insight behind SVMs is the concept of the optimal hyperplane. Rather than just finding any line that separates the classes, SVM finds the one that maximizes the margin between them. Let me explain what margin means. When we draw our decision boundary, which is called the hyperplane, we can also draw two parallel lines on either side. These parallel lines pass through the closest data points from each class. The distance between these two parallel lines is what we call the margin. Think of it like a road running between two neighborhoods. The hyperplane is the center line of the road, and the margin is the width of the road itself. A wider road means more safety margin. If a new data point comes in slightly off course, a wide margin gives us more room for error before we misclassify it. The SVM algorithm specifically looks for the hyperplane that creates the widest possible margin. This is why you'll often hear the phrase maximum margin classifier when people talk about SVMs. The formula shows that we want to maximize 2 divided by the magnitude of W, where W is the weight vector that defines the orientation of our hyperplane. This maximum margin approach is what gives SVMs their excellent generalization ability. By creating the largest possible buffer zone between classes, we get a classifier that's more robust to noise and performs better on new data.
Now let's talk about one of the most important concepts in SVMs: support vectors. These are the data points that give the algorithm its name, and understanding them is crucial for any interview. When we look at our data with the hyperplane and margin drawn, something interesting happens. Notice that most data points are far from the decision boundary. They could move around quite a bit without affecting where the boundary sits. But there are a few special points that lie exactly on the margin lines. These are the support vectors. Support vectors are the critical pillars that hold up our decision boundary. If you were to remove any of these points, the hyperplane would have to shift to find a new maximum margin. But if you remove any of the other points, the ones that are further away from the margin, the hyperplane stays exactly the same. This property has a profound implication. When making predictions with an SVM, we only need to consider the support vectors. All the other training points become irrelevant. This makes SVMs memory efficient, especially when dealing with large datasets where only a small percentage of points end up being support vectors. In our visualization, you can see the support vectors glowing and connected to the hyperplane. These few points completely determine the position and orientation of our decision boundary. This is what interviewers often refer to when they ask about the sparse solution property of SVMs.
Let's get into the mathematics behind SVMs. Don't worry, I'll break it down step by step so it's easy to understand. The hyperplane is defined by the equation w.x plus b equals 0. Here, w is the weight vector that points perpendicular to the hyperplane, x is any point on the hyperplane, and b is the bias term that shifts the hyperplane away from the origin. For classification, we use this hyperplane to make predictions. Points on one side where w.x plus b is greater than or equal to 1 belong to class positive 1. Points on the other side where w.x plus b is less than or equal to negative 1 belong to class negative 1. Now here's the key insight about the margin. The distance from the hyperplane to the margin boundary is 1 divided by the magnitude of w. Since we have margins on both sides, the total margin width is 2 divided by the magnitude of w. To maximize this margin, we need to minimize the magnitude of w. In optimization terms, we typically minimize 1/2 times w squared, which is mathematically equivalent but easier to work with because it's a smooth convex function. This gives us a quadratic programming problem with linear constraints. The beauty of this formulation is that it's convex, meaning there's only one global optimum and we're guaranteed to find it. This is why SVMs are so reliable in practice. Now, let's discuss the hard margin SVM, which is the simplest form of the algorithm. This works when your data is perfectly linearly separable, meaning you can draw a straight line or hyperplane that completely separates the two classes with zero training error. In our visualization, you can see a clean data set where all blue points are on one side and all orange points are on the other. The SVM finds the maximum margin hyperplane, and every single point is correctly classified. The check marks appear next to each point, and our accuracy counter hits 100%. This sounds great, but here's the catch. Hard margin SVM has a strict requirement. Not a single point can violate the margin. Every data point must be on the correct side of its respective margin boundary. In the real world, this is extremely limiting. Real data sets are messy. They often have outliers, noise, or classes that genuinely overlap. If even one point from class A falls on the wrong side of the margin, hard margin SVM fails completely. It cannot find a solution. This sensitivity to outliers is a major weakness. Imagine you have thousands of perfectly separable points, but one single outlier is in the wrong place. The entire algorithm breaks down. This is why hard margin SVMs are rarely used in practice. Instead, we need a more flexible approach that can handle some misclassification while still finding a good decision boundary. To handle real-world data that isn't perfectly separable, we introduce soft margin SVMs with slack variables. This is what most implementations of SVM actually use. The idea is simple but powerful. We allow some data points to violate the margin or even be misclassified, but we penalize them for doing so. Each violating point gets assigned a slack variable denoted by the Greek letter xi. If a point is correctly classified and outside the margin, its slack is 0. If it's inside the margin but still on the correct side, the slack is between 0 and 1. If it's actually misclassified, the slack is greater than 1. The sum of all these slack values represents the total amount of violation in our model. This brings us to the crucial parameter c, which controls the trade-off between two competing goals. On one hand, we want to maximize our margin, like before. On the other hand, we want to minimize the total slack, meaning we want to minimize misclassification. When c is low, we're saying we don't care much about individual misclassifications. The algorithm will allow more errors to achieve a wider margin, creating a smoother, more general decision boundary. When c is high, we're heavily penalizing every error. The algorithm will try hard to classify every training point correctly, even if it means a narrower margin or a more complex boundary. This can lead to overfitting. Finding the right value of c is a critical hyperparameter tuning decision that usually requires cross-validation. Now we come to one of the most elegant ideas in machine learning, the kernel trick. This is what allows SVMs to handle non-linear decision boundaries. Consider a dataset where the classes are arranged in a circular pattern. The blue points form a cluster in the center, and the orange points surround them in a ring. No matter how many straight lines we try to draw, we simply cannot separate these two classes. Every linear boundary fails, as shown by the red X marks. Here's where the magic happens. What if we could lift these data points into a higher dimensional space? In our example, we transform from 2 dimensions to 3 dimensions by adding a new feature. A common transformation is to add the sum of squares of the original features as a third dimension. When we do this, something remarkable occurs. The center points, which have smaller values, don't get lifted as high. The surrounding points with larger values get lifted higher. In this new three-dimensional space, the two classes become separable by a simple flat plane. The key insight is this: a non-linear boundary in the original space corresponds to a linear boundary in the transformed space. The SVM only needs to find a linear separator in the higher dimensional space, which it's already great at doing. But here's the really clever part. We don't actually need to compute the transformation explicitly. The kernel function allows us to compute the dot products in the higher dimensional space directly from the original data. This is computationally much cheaper and is why it's called a trick. Let's explore the most commonly used kernel functions. Each kernel represents a different way of measuring similarity between data points in a transformed space. First, we have the linear kernel, which is simply the dot product of two vectors, x dot y. This is equivalent to not using any transformation at all. It creates straight-line decision boundaries and works best when your data is already linearly separable. It's also the fastest option computationally. Next is the polynomial kernel, defined as x dot y plus c, all raised to the power d. The parameter d is the degree of the polynomial. A degree of 2 creates quadratic boundaries, degree 3 creates cubic boundaries, and so on. Higher degrees allow more complex curves, but risk overfitting. The RBF kernel, also known as the Gaussian or radial basis function kernel, is by far the most popular choice. Its formula is the exponential of negative gamma times the squared distance between 2 points. RBF can model extremely complex decision boundaries and works well for most problems. This is usually the default choice when you don't know what kernel to use. Finally, we have the Sigmoid kernel, which uses the hyperbolic tangent function. This kernel is related to neural networks and creates S-shaped decision boundaries. It's less commonly used than RBF, but can be effective for certain types of data. Each kernel essentially gives the SVM a different lens to view your data. The choice of kernel depends on the structure of your problem and usually requires experimentation to find the best fit. Let's take a deeper look at the RBF kernel's gamma parameter, which is one of the most important hyperparameters to understand for interviews. The gamma parameter in the RBF kernel formula controls how far the influence of a single training example reaches. You can think of it as defining the radius of influence for each data point. When gamma is low, say 0.1, each data point has a large radius of influence. The decision boundary becomes very smooth and simple, almost like drawing a big circle around each class. The problem is that with such a smooth boundary, you might miss important patterns in your data. This is underfitting. The model is too simple. When gamma is at a medium value, around 1, you get a balanced decision boundary. It follows the general shape of the data distribution without fitting to every individual point. This is often the sweet spot where the model captures the true underlying pattern. When gamma is high, say 100, each data point's influence is very localized. The decision boundary wraps tightly around individual points or small clusters. While this might give you high training accuracy, the model is essentially memorizing the training data rather than learning generalizable patterns. This is overfitting. The model is too complex and will perform poorly on new data. The key insight is that gamma acts like a zoom level. Low gamma gives you a bird's-eye view that sees broad patterns. High gamma zooms in so close that you see every tiny variation, including the noise. Now, let's see how C and gamma interact with each other. This is crucial because tuning only one while ignoring the other often leads to poor results. We can visualize this as a 2x2 grid. On one axis, we have C, the regularization parameter that controls how much we penalize misclassification. On the other axis, we have gamma, which controls the complexity of the decision boundary. In the top left corner, with low C and low gamma, we get a very simple, smooth boundary that allows many errors. This represents high bias and is likely to underfit. In the top right corner, with low C and high gamma, something interesting happens. We have complex local boundaries because of high gamma, but low C means we don't penalize errors harshly. The result is a strange mix of local complexity with overall flexibility. In the bottom left corner, with high C and low gamma, we get a nearly linear decision boundary that tries hard to classify every point correctly. This works well if your data is actually close to linearly separable. In the bottom right corner, with high C and high gamma, we have both high boundary complexity and strong error penalization. This almost always leads to overfitting. The model creates complex contours that perfectly wrap around each training point but fail to generalize. The practical lesson here is that you need to tune C and gamma together. The best approach is to use grid search with cross-validation. Try different combinations of C and gamma values and see which pair gives the best validation performance. The code snippet shows how to do this using scikit-learn's grid search CV function.
SVMs are inherently binary classifiers, but most real-world problems have more than two classes. So how do we extend SVM to handle multiple classes? There are two main strategies. The first is one versus rest, also called one versus all. For a problem with k classes, we train k separate binary classifiers. Each classifier learns to distinguish one class from all the others combined. So if we have three classes, A, B, and C, we train three classifiers, A versus not A, B versus not B, and C versus not C. During prediction, we run all k classifiers and assign the point to whichever class gives the highest confidence score. The second strategy is one versus one. Here, we train a classifier for every pair of classes. For k classes, that means k times k minus 1 divided by 2 classifiers. With 3 classes, we'd have 3 classifiers, A versus B, A versus C, and B versus C. During prediction, all classifiers vote, and the class with the most votes wins. Which approach is better? For SVM specifically, one versus one is often preferred. While it requires more classifiers, each classifier is trained on a smaller subset of data, making training faster. The voting mechanism also tends to be more robust. The comparison table shows that for 10 classes, one versus rest needs 10 classifiers each trained on the full dataset, while one versus one needs 45 classifiers each trained on much smaller subsets. In practice, one versus one often trains faster and gives better results.
Let's wrap up with the key points you need to know for technical interviews. These are the questions that come up again and again. Why maximize the margin? A larger margin provides better generalization by creating a safety buffer. Even if new data points are slightly different from training data, a wide margin reduces the chance of misclassification. What are support vectors? They are the critical data points that sit exactly on the margin boundaries. They completely determine the decision boundary. Remove them and the hyperplane changes. Remove other points and it stays the same. When should you use RBF versus linear kernel? Use linear when your data is linearly separable or when you're working with high-dimensional sparse data like text features. Use RBF when you have complex nonlinear patterns to capture. How does the C parameter affect the model? High C creates a strict classifier that heavily penalizes errors, potentially leading to overfitting. Low C creates a softer classifier with a wider margin that tolerates some errors, which can be more generalizable. On the pros side, SVMs work great in high-dimensional spaces, are memory efficient since they only store support vectors, and the kernel trick gives incredible flexibility for modeling complex boundaries. On the con side, SVMs don't scale well to very large datasets, require careful feature scaling, and don't naturally output probability estimates. They work best for small to medium datasets with clear class separation. If you found this video helpful, please like and subscribe to the channel for more AI and machine learning content. Thanks for watching, and good luck with your interviews.